Hello everyone, welcome to my channel Physics Infinity. I'm going to talk about the complete story of dipole today. A very important topic for you. Dipole basically is a simple electrical system which has minus q and plus q charges separated from each other by a very small distance. The significance about learning the physics of dipole is enormous in physics because we would like to know how the different materials behave when they are in electric and magnetic fields, when they are put in electric and magnetic fields. And dipole, understanding of the dipole, the physics of the dipole helps us to understand the behavior of the electrical and magnetic properties of the materials. Now remember, the atom or a molecule is fundamentally electrically neutral. But in terms of, if we think it in terms of electrically, then it has electrical as well as, it has positive electrical as well as negative electrical part. Of course, I am talking of the nucleus which has the protons and the neutrons, and that is positive, and then the electrons which are orbiting around the nucleus, the negative part, electrically negative. And together, well, the net result electrically, the atom or a molecule remains neutral. But suppose if we have separated the electric, the negative and the positive part slightly, then overall it remains electrically neutral, but we get a dipole. So a dipole would have a plus charge q and a minus charge q separated from each other by small distance d. Now before I proceed on with the discussion of the entire physics of dipole, the intensity, the potential, the torque, the potential energy and the interactions and so on, let me first make you understand about the dipole as a system. So here we are, minus q and plus q separated by small distance, that is, if this is kept at A, minus q is at A and this is at B, then AB is called the dipole arm, and AB is equal to D, and at A we have minus q and at B we have plus q. So overall electrically neutral, and this D or AB is very, very small. Look, we are talking of atomic and molecular dimensions that will run into Armstrong. So they are very, very close to each other. Nevertheless, the line joining A to B, this is called the axis of the dipole. O is the midpoint of dipole. Now, midpoint of the dipole also has a lot of significance because all distances, all positions of any other point from the dipole is going to be measured from O. Remember that. So when I say that this point is so much away from dipole, technically it is away from O. It is away from O. So all distances, the position vectors of every point from the dipole would be from O. Fine. The perpendicular bisector of the dipole arm, AB is the dipole arm, that is called the equator. Surely the equator will pass through O and it is perpendicular to the line AB, the dipole arm AB. Right. Now, when we talk of intensity, potential, torque, potential energy and everything, every property of the dipole, every behavior of the dipole is understood in terms of a very important parameter, that is called dipole moment. Okay, we can call it electrical dipole moment because later on in the chapter of magnetism, we also learn about magnetic dipole, but I won't touch it right now here. So the electric dipole has electric dipole moment, and all the properties and behavior of the dipole are understood in terms of the dipole moment. This is denoted by small p. So, and it's a vector, small p arrow, and that is, the magnitude is q into d. That is q multiplied by the dipole arm qd, and the vector p arrow, the dipole moment vector, is from minus q to plus q, that is from A to B. So that is along d arrow. So small p arrow is qd arrow, And for the time being, I'm assuming my dipole is lying, the dipole axis is along x-axis. The dipole axis is along x-axis. Okay, so in that case, I can say that P arrow will be Q D I cap. Right. I would be first of all interested in a point P, whose position vector from the dipole. That means position vector from O, because O would be treated as the origin of the dipole. That is OP arrow. So R arrow is OP arrow, and certainly my first thing would be to find the potential and the intensity at the point P. I am taking a general point, and then we'll come to the special cases. The general point, so the position vector of P, that is OP arrow, makes an angle theta, with the dipole axis, Now let's start. Well, that's sort of our page 1. So potential at P, of course, it's a simple electrical system having minus Q and plus Q. So I'll have potential contributions both from minus Q and plus Q, and then I'll take the scalar sum as usual, simple electrostatics. So KQ by R1 from the positive charge minus KQ upon R2 from the negative charge minus Q, and I get KQ R2 minus R1 upon R1 into R2. Keep it. Well, because D is very, very small, so R1 and R2 can be approximately to be equal, and R2 minus R1. So if I drop a perpendicular from B on the position vector, it will be something like this. Okay, let me call that S, and that AS. So I can write here AS would be R2 minus R1, and that will be D cos theta. So if I look at this right angle triangle, well, of course this is 90 degrees in this right angle triangle. So AS is R2 minus R1, this is D, so R2 minus R1 is D cos theta. Exactly, that's what I do here. So V is KQ, R2 minus R1 is D cos theta, R1, R2 I approximately take equal to R, and that will be, of course, because the dipole is very, very small, so R1, R2 approximately equal, that makes R square. So I get a neat expression for the potential Kp cos theta upon R square. K as usual, though I don't have to say, is, well, you all know that, well, K is 1 by 4 pi epsilon naught. K is 1 by 4 pi epsilon naught, the electric field constant. Now here you notice one thing, that V is a function of R and theta. Just keep it in mind, because I am going to use this function in order to get electric intensity by taking the negative derivative of the potential. But the potential is a function of R and theta both. So I'll have to take the partial derivatives in order to get the electric intensity. So here we are. The electric intensity, we think in terms of two parts. The radial part, that is along the radius, look at that, and we call it ER. And ER will be minus dV upon dr. Now this curly D that I write is for the partial derivative. Now technically, when we write dV by dr, I should put a theta here and then equal. Now this bar theta means that when I am taking the derivative of V with respect to R, I am keeping theta constant. Remember that. So and the partial derivatives is the curly D, not the straight D. So curly D. So partial derivative of V with respect to R gives me ER. Technically this also I should write curly ER, but okay, that's okay. So I take the derivative of this and I keep theta constant, so I get 2 Kp cos theta by R cube. So ER is 2 Kp cos theta by R cube. Fine. Potential gradient, negative of the potential gradient, that's what I have used, the fundamental relationship between potential and intensity. Now let's talk about the azimuthal component of electric intensity. That is represented as E theta, azimuthal component, radial component, azimuthal component. Now azimuthal component, many students have the misconception, sir it should be minus dV by d theta. No, no. D theta is not distance. That won't make that won't make potential gradient if I take dV by d theta. So I have to take on this line perpendicular to ER, this part that is let us say, because S I have taken here, so I can take this as, let's say, PT or P, well, whatever, PE. So PE would be R d theta. Well, this is R, this is d theta. So this part is R d theta. So the potential gradient along this line perpendicular to the radial, that would be taken as R d theta. And once again here I have taken R constant, so I take this as bar R, means R is taken as constant. So I take the negative derivative of the potential function with respect to R is a constant, so dV upon d theta. When I take, I get the simple answer, that is Kp sin theta by R cube. Beautiful. I've got two components of the electric intensity at P, the radial compo, that is this 2 Kp cos theta by R cube, and the azimuthal compo, which is perpendicular to ER, that is Kp sin theta by R cube. Very easy job now. I have to find E at P. So this is E at P. E at P would be square and then take the under root. So ER square plus E theta square under the root. I just do this, square, add, take the root, I get the answer Kp by R cube 3 cos square theta plus 1 to the power half. Remember, this is the general expression of the electric intensity at the point P, whose position vector from the dipole, that is OP arrow, is equal to R arrow. Fine. Now, I also would like to know what angle E makes with the radial compo or along the radius vector. Suppose this angle is phi. So very easy, simple, our knowledge of vectors help us. So tan phi, I can see tan phi is E theta upon ER, E theta upon ER, and I just put the values from there. It is half tan theta. Therefore phi is equal to tan inverse 1 half tan theta. So I know everything about the electric intensity, its magnitude as well as direction from the radial vector, that is okay. Now I be a little more specific. If the point is on the axis, if the point is on the equator, let's go one by one. So if I take on the axis, theta can be 0 when the point is here, or theta can be 180 if the point is to the left of A, 0 degree or 180 degree. I just put the values. So V can be Kp by R square and E would be 2 Kp. I put the value theta or 180 degrees here, same thing, I get 2 Kp by R cube. So expression for potential and intensity at a point on the axis. At a point on the axis, when I talk of, it could be on the right of B or it could be on the left of A. Done. Let's now talk about on the in terms of vector. Remember that E arrow on the axis is always parallel to the dipole moment vector, is always parallel to P arrow. Let me now take on the equator. And on the equator, theta can be either here, the point can be either here or here. That means theta can be either 90 degrees or third quadrant, that is 270 degrees. So when I put theta equal to 90 degrees or 270 degrees in the expression for V and E, I get the magnitude. So V is 0, V will be 0 and E will be Kp by R cube. So the magnitude of the electric intensity at a point on the equator, which could be either here or here, is always Kp by R cube. But the direction, so on the equator, the field would be here and opposite to P arrow, and here it is here opposite to P arrow, because definitely P arrow is here. So there you are. So we have learned everything. We have learned about the potential. Suppose the dipole with the dipole moment P arrow is placed in a uniform external electric field of strength E arrow, where E arrow is along x-axis, so I can take E arrow as EI cap. And we place the dipole within this field, Then within the field, the dipole has potential, the dipole field system has potential energy U that is equal to minus P arrow dot E arrow. So that will be minus PE cos theta. If theta is the angle that the P arrow dipole moment vector makes with the electric intensity vector, the electric field vector. From this expression, we can see very well that the minimum potential energy, that is UO, will be when theta is equal to 0 degree. When theta is equal to 0 degree, and that will give me minus PE. And this is what we can say is the most stable state. This is the most stable state of the dipole. In the theta state, the dipole is excited state, and theta equal to 0 degree is the PE state, because is the stable state, and in the stable state the system, the dipole field system would have least potential energy, and that is equal to minus PE. In the excited state, it is minus PE cos theta. Now just see here. So if E arrow is like this and the dipole is like this, and if I external agent, turn it like this, turn the dipole like this, that is bring it from the least PE state to an excited state, then look at that, my muscles. I have to do work. And then the work done by me, that is I am the external agent here, to take the dipole from theta equal to 0 degree state to the theta state, that will be delta U, the change in the potential energy, that is U theta minus UO. So minus PE cos theta minus PE plus PE, that will become PE into 1 minus cos theta. Once the dipole is in the excited state, then on plus Q, there is a force F arrow, there is a force F which acts along the field, and a force F which acts against the field, and these two forces creates the steering effect, constitute a couple, and the moment of couple is torque. So if the dipole is in the excited state in the field, then automatically there would be a field torque that will act on the dipole so as to bring the dipole to the least PE state, So like this. And in the excited state, the torque on the dipole will be, of course, 1 of the force multiplied by the perpendicular distance. So that will be F multiplied by d sine theta. So that will be F into d sine theta. I have not written on the board here, but I can explain you. So the torque would be F into d, 1 of the force multiplied by the lever arm. So from here to here, that is d sine theta. So I can say that torque somewhere here. So alright, okay, that will be F into d sine theta. Now F is QE. Now Q into D is P, so it is PE sine theta. Very easy. So just one step. So the torque acting on it will be PE sine theta, or in other words, tau arrow will be P arrow cross E arrow. The tau arrow will be P arrow cross E arrow. There you are. Tau arrow is P arrow cross E arrow, that is PE sine theta, and clockwise rotation. So if there is an axis perpendicular to the plane of the board, that is along minus z axis, then about torque is an axial vector. So the torque would act along minus k cap inwards. The torque would be, I can say, circle cross, that means inwards. So it is minus PE sine theta, and this we are going to show is a restoring torque. Sure, it is a restoring torque because it is trying to restore the dipole to the minimum potential energy position. I can, if theta is very, very small, then sine theta is equal to theta in radians. So I can write the restoring torque as P E theta. P is constant, E is constant. So I can say this restoring torque as Hooke's torque, just like Hooke's force. So Hooke's torque. And this K, capital K slash, I call the Hooke's constant, and the Hooke's constant here is P into E. Once we have done that, so normally dipole, while coming here, because of inertia, will overshoot. Then torque will act anti-clockwise, then clockwise, then anti-clockwise, clockwise, and the dipole would begin to execute angular oscillation within the field. If theta is small, we can show that this angular oscillation is angular SHM, because the restoring torque in the disturbed position, excited position, I have shown is Hooke's constant, so K slash multiplied by theta. If that is so, then we know that from our knowledge of the simple harmonic motion, that this executes angular SHM of angular frequency K slash divided by I, where I is the moment of inertia. I is the moment of inertia of the dipole about an axis passing through O, perpendicular to the plane, Okay, so I get omega as I replace K slash as P into E upon I, and the time period, of course, is 2 pi upon omega, the time period of the angular SHM. 2 pi upon omega, that is 2 pi I upon interaction between dipole. So I have two dipoles or dipole moments, P1 and P2, where you can have various positions by which we can place these dipoles and then find the interaction between them. Let me tell you the simple technique that I am going to use. Dipole 2 is in the field of dipole 1. Therefore, dipole 2 and dipole 1 will have electrical PE. And the negative gradient of that negative PE will give me the force. So I use the basic fundamentals. Now in order to explain you this of how to calculate the interaction, I take two specific situations, and then you can do any problem dealing with the interactions between two dipoles, because the technique would remain the same. Fine. My first situation is the dipole 1 and the dipole 2 are placed such that in the xy plane, such that P1 arrow and P2 arrow are parallel. The dipole moments are parallel and the dipoles are separated by distance r in space. Well, if I look at this, then P1 arrow is along j cap and P2 arrow is also along j cap. The dipole 1 creates electric field at the site of 2, and therefore between the two dipoles they will have interactive force because of the interactive potential energy. Now the interactive potential energy U21, look at the symbol itself. This is the potential energy of the dipole 2 in the field of the dipole 1. Now we know the general expression for U we have done earlier, that is minus P dot E. So minus PE cos theta, So U21 will be minus P2, and the field of the dipole 1 at the site of the dipole 2. Now this dipole is on the equator of the dipole 1. So the E12 arrow will be opposite to P1 arrow, opposite to P arrow. That means theta will be 180 degrees. So here you are. Well, that gives you minus plus. So, and E12 on the equator is Kp by r cube. So I just put down that value. So K P2 P1 by r cube. Then I want to find the interactive force between the two. So force on the dipole 2 due to the field of dipole 1, that will be minus potential energy gradient U12 upon dr. I just take the derivative of this, I get 3k P1 P2 upon R to the power 4. The positive sign basically here tells you that there is repulsion between the two, and quite logical also. You can just think of, because this will be minus Q1 here and minus Q2 here, repel, plus Q1 plus Q2, repel, and the negative and the positive are much further away. So overall, physically also you can reason that there would be repulsion between the two dipoles, and the very fact that the interactive force is coming out to be positive means this is a case of repulsion. The two dipoles get repelled. The second situation I take when the two dipoles are placed such that P1 arrow is parallel to P2 arrow and both lie on the xy plane, and I can show you here that as the situation I have taken, P1 arrow and P2 arrow is along I cap. The midpoints, that is the O's of the dipole, are separated by R, and we wish to find. So once again, I will find the interactive potential energy of the dipole 2 due to the field of 1, and then to find the interactive force, I'll take the negative energy gradient with respect a negative energy gradient that will give me the interactive force. U21, the potential energy of 2 due to the field of the dipole 1, minus P arrow dot E arrow. So minus P2 E12 cos 0 degree. Mind you, the dipole 2 is on the axis, of the first dipole. So theta would be 0, cos 0 degree would be 1. So this will become minus, and on the axis we have done earlier, the field value is 2 kp by x cube, 2 kp by r cube, sorry. So minus 2 kp minus 2k P2 P1 by r cube. The interactive force, I take the negative potential energy gradient, I take the derivative of this, I get the answer minus 6k P1 P2 upon R4. The minus sign here tells you that overall the dipoles are getting attracted. They are getting attracted, and you can see that quite well, because minus charge here, plus charge here, minus charge here. So the plus charge and the minus charge are closer, whereas the minus charge and the minus charge and the plus charge and the plus charge are away. So overall, we do expect attraction between the dipoles, and mathematics also tell us that, so we are satisfied. Now let's come to the conclusion. You have noticed that in the case of dipole, the potential is proportional to 1 by r square. Remember, kp cos theta by r square. Intensity proportional to 1 by r cube. On the axis 2 kp by r cube. On the equator kp by r cube, etc. And the interactive force between the dipoles is proportional to 1 upon r4. Now this information, this knowledge also can help you in tackling some of the questions that you face in the competitive examinations. I hope you have enjoyed the video. Do subscribe.
If you love the video and want me to make more useful videos for you, subscribe my channel and hit the bell icon to stay updated.